VLSI testing and analysis. So let's start with unit number 6. Okay, fine. So before we start speaking about these topics such as types of faults, need of DFT, fault models, BIST, etc., we need to understand that how much important it is to test a chip before it is actually put into either a system, and that before a system is actually commercialized for sale. Okay, so um, just like I was just talking with one of my friends who works with Tata Motors, and I was just asking him that, any automobile manufacturer, um, what is the most important activity before the car is launched into the market? He was telling me in 3 words. He was telling testing, testing, and testing. So he told that no matter how excellent an engineering marvel your car is, but if you do not put it to test on a test bed, you really cannot ensure that after that car is actually put on road, how will it actually perform? That is why no matter which engineering stream we are talking about, whether it is civil engineering, electrical engineering, mechanical engineering, production engineering, anything, even computer and IT people also, before they send the final copy of the finished tool or the product to the customer, they have to actually rigorously test it by giving all possible inputs which the customer can give, and then they test that what kind of output it is. So testing is an inseparable, uh, compulsory, and the final step before any system is actually put into the field. That is called as putting the product in the field. So to just cite an example, I will give some statistics, so you will understand what is the importance of testability here. So in the year 1994, our microprocessor pioneer Intel, they sent Pentium chips to IBM. So in those years, IBM was the person who used to take Intel's processors and put them into machines. So in 1994, Intel sent Pentium chips to IBM to be put in their desktop PCs. And the design engineers found that there was a error in the floating point divider unit. So it was found that there is an error in the chips floating point divider unit, or you can say FPU, floating point unit. But it was good that they communicated it to IBM, so IBM did not put it. But you'll not believe that due to this mistake, can you imagine what is the loss incurred by Intel? Intel incurred a loss of $450 million. Intel incurred a loss of $450 million. So just ask Google how much is $450 million. It is equal to INR 33 billion. Can you imagine? And this happened before 26 years. It was INR 30 billion way back in 1994. So you see here, so if a particular chip is not tested properly and when it goes into the market, this is the loss which is incurred to the manufacturer. So we would like to mention that any chip or wafer can be tested or on many different platforms, right? So now we go gradually into the concept of design for testability or why it is required. Okay, so understand one thing, that IC tests fall into three main categories. We say that IC tests are divided into the following three. So the test number one said it is done before IC tape out. What is tape out? That is, tape out is nothing but technical word used by foundries for indicating IC manufacturing or fabrication. We told that we do not say that IC is manufactured, we say that IC is fabricated. So it is done before IC tape out. That is fabrication. It is done before IC tape out or fabrication, and it is is intended to verify the functionality of the circuit, nothing more. Intended to verify the functionality. Hence, it is also known as functionality test or logic verification. So it is called as, so test number one is called as functionality test or logic verification. Or functionality test or logic verification. Then we have test number two. So after the design has been fabricated and converted into an integrated circuit, we perform the second test. So test number two, it is done on the first batch of chips. After tape out, and the test is done at full speed. Okay, so this test number two is done at full speed. So in test number one, you just verify whether it is functionally correct, but you do not stretch the design to its limit. So it is done at full speed of the system. That means the system is intended to perform at 2 gigahertz. Then you are going to apply a clock of 2 gigahertz and then test the system. Okay. Now near test number three. The test number three, it verifies that every transistor, gate and storage element is functioning correctly. Here what we do, that we check if each transistor, gate and storage or memory element is working correctly. Okay, so they are also known as manufacturing tests. They are called as manufacturing tests. Okay, so testing of a chip can occur at the following 5 levels. Testing of a chip can occur at the following 5 levels. First, wafer level. Second is packaged chip level. That is IC level. Third, board level. Fourth, system level. And fifth is field level. Okay, now let us understand that what is the cost incurred when a particular fault or an error is found at any of these 5 levels. Okay, so now we will see that the cost of a fault when detected at different levels. Okay, so what is the cost incurred to a IC manufacturing company if the fault is detected at wafer level, package chip level, board level, system level, and field level? Okay, so here we'll come to know. Okay, so wafer level, if a fault is there, the cost is approximately $0.01 to 0.1. If the fault is found at package chip level, the cost now varies from $0.1 to $1. Board $1 to 10. System level fault detection $10 to $100. And the field level, it can go from $100 to $1,000. This is what happened with Intel, as I mentioned, 1994. In the field level, the error was there and it had to pay a very large amount. That is why earlier a fault is detected, it costs less and it can be rectified also. Otherwise, it goes on increasing exponentially. That is what is the main importance of testing. Okay. Now, let us understand what are the parameters based on which any IC manufacturer, may it be Qualcomm, MediaTek, or Intel or AMD, on what basis the cost is actually calculated. So the price of an IC depends on two factors. First is the cost of manufacturing, and second is the profit margin. How much profit does the manufacturer intend to earn after making that IC? Okay, it's very important. And understand that the price of an IC, it also goes on reducing with volume. That is important. So price of an IC reduces as volume increases. And there are basically three components, like we have three components to power dissipation: static power dissipation, dynamic power dissipation, short circuit power dissipation. Similarly, understand that the recurring cost of an IC R is made up of the components R equal to R package plus R test plus R process. Okay, so packaging cost, testing cost. So this is the cost of testing a chip. This is actually fabrication, and this is the packaging cost. It's very important. And there is lot of mathematical modeling based on statistics and economics which has been done. To summarize, we can say that the yield of an IC is very important. So if you remember in our introduction to VLSI field, we had this thing. Okay, so we had this thing representing a silicon wafer, and we told that if this is the silicon wafer, then this is the diameter, and the diameter of silicon wafers is 12 inches, thickness is a few microns. So this shape is cut into small squares. Similarly, we have so every square here, okay, one microprocessor each. So a microprocessor is fabricated inside each square, and you know that chips are always square in size. So naturally we see here that these portions are all wasted. Okay, so this 12-inch circle is called as a wafer, and the number of good chips divided by the number of chips on the die is called as a yield. That is what we know. Okay, so this is called as a good die, and others are called as bad dies. So it is called as yield. So the yield of a wafer is defined like this. So why, what is the spelling of yield? YIELD. The yield Y is equal to the number of good die, number of good or working die divided by the total number of die per wafer. So this value of yield can be calculated only after testing. Okay, so this particular parameter, number of good die, can come only after testing. So you want to calculate the value of yield of a wafer, we need to test the individual chips. It's very important. Okay. Now there are some important aspects of testing which we'll cover. And there are some terms which we need to understand. There's a difference between the terms verification, validation, and testing. So there are fine differences which you can mention. So verification basically refers to formal proof of correctness. This is some English literature. Validation basically refers to techniques which increase the confidence in correctness. Techniques which increase confidence in correctness. So simulation can be called as a validation tool. Simulation is an example of a validation technique. And then we have testing. So we can say testing is a final proof of correctness. Okay. And from this testing, which actually gives us a final proof that yes, our design is correct on different levels, such as wafer level, packaged chip level, board level, system level, and field level. That means we have to design our chips in such a way that they can be easily tested. That is a design for testability. So in layman terms, how can we define design for testability? Design for testability is defined as a design which also has an inherent ability to be tested. So we will define it now. So DFT, we have design for testability. DFT. So we can say that design for testability is an approach. So it is a design approach which incorporates the ease of testing the chip in addition to achieving the desired functionality. In addition to, okay, so it is a design approach. So DFT, design for testability. It is a design approach which incorporates the ease of testing the chip in addition to achieving the desired functionality. That is why initially when the chips were very small, say small scale integration or medium scale integration, at that time the design was only focused at achieving the functionality. But as and when the ICs have become more and more complex and millions and billions of transistors got started getting fabricated in a very small area, at that time the designers understood that once the IC is fabricated, it is just not humanly possible to test the chip. That is why along with the design team there was a testing team which used to put certain blocks inside the IC design in the architecture, so that even after the chip is manufactured it was easily testable. Got the point? So the science of testing an IC has evolved greatly as integrated circuits have evolved both in size, in complexity, and also the number of transistors which have been fabricated. That so if you read some books like Malvino Leach, RP Jain in second year, they have a chapter dedicated for testing. There they have something called as bed of nails testing. Then you have probing. So many techniques were used, but as and when the number of transistors started increasing, this bed of nails testing, voltage probe testing, all of them proved to be very inefficient, and they had to come out with special design approaches which we call as design for testability. Got the point? So this particular approach makes the design easily testable. Okay, so we can say DFT makes ICs easily testable. Now question comes to your mind that are there any standards, IEEE standards for DFT? Yes, they are. So when you speak about DFT or design for testability, there are many terms which are used such as boundary scan, JTAG, etc. So all these terms you have heard, but you never knew that they are having connection with this topic of design for testability. Okay. So always understand that a particular chip may have excellent design, but does not mean that it is also having excellent testability. So please understand this thing. Okay, so that is why we make a point that all chips which are all chips which are designed need not be testable. It's not compulsory. Okay. So IEEE standards exist. IEEE standards exist for the concept of DFT. Okay, so boundary scan JTAG. So you must be knowing that JTAG stands for Joint Test Activity Group. So we have joint test activity or action, anything. So let us write the numbers. So boundary scan is just like we say that VHDL 87 was IEEE STD 1076 and VSGL 93 is IEEE STD 1164. Similarly, Verilog is IEEE STD 1364 and Firewire bus is IEEE STD 1394. So all the technologies which have been commercialized and are used in products are all standardized by IEEE. So we have boundary scan IEEE STD 1149. It is also called as boundary scan protocol. Similarly, this JTAG cables which we use for programming Raspberry Pi or ARM or whatever it is, or FPG also, in fact, they are all conforming to a substandard of boundary scan protocol. That is, its number is 1149.1. So JTAG has the IEEE number IEEE STD 1149.1. You can check it. Okay, so boundary scan and JTAG, and it's IEEE STD 1149 and JTAG is IEEE STD 1149.1. Okay, so there are many kinds of scans. Similarly, as I said, that different techniques have existed right from the time testability was found to be critical and crucial in IC design. They are like different approaches. Voltage probing, then we had bed of nails testing. It's also called as test fixtures. Test fixtures. Okay, then we had a test bed, that is a testing PCB. Okay, it's called as test bed. PCB testing. For bench level testing, and then we have PCB with chip in SITU. Okay, for system level testing. Board level. Okay, fine. And we also have test programs, that is programs which generate the appropriate test vectors. So test programs are special programs. They are not training programs, huh? These are actually codings. So special programs which generate the right test vectors to test all functional paths in the design. Okay, and then in different approaches to testing, we have BIST, that is built-in self-test. I have ATPG, that is called as automatic test pattern generation, ATPG. And then we have boundary scan, and we have TAP. All of them are a part of our syllabus. So BIST, ATPG, boundary scan, TAP, probing, bed of nails, PCB testing, system level testing. Okay. Now we come to the next classification, which is called as type of faults. Okay. Is my screen visible again? There was a disconnection.
Yes, sir.
Okay. So now we come to the most important topic called as types of faults, which also exclusively asked in the exam many times. Faults are classified in many types. So we have physical, electrical, and we have logical faults. So understand that because of physical faults in design or in the fabrication, it ultimately leads to both electrical faults and also logical faults. So physical faults is a cause and electrical and logical faults is an effect, but ultimately they are faults. So some examples of physical faults are process variations during fabrication, then we have defects in silicon substrate, then we have photolithographic defects, photolithographic defects, we have mask contaminations, and we have oxide effects, not effects, defects. And due to this, the different electrical faults which occur are shorts, opens, that is short circuit and open circuit. If you want, we can short circuit, open circuit. So then we have transistor stuck on, and we have transistor stuck off. Then we have resistive, open and short, etc. Okay. Logical faults, we have many, but we will not discuss all. So logical faults, we have stuck at 0. It is technically written as SA0 fault. Then we have stuck at 1 called as SA1. It is written as SA1 faults. Then we have delay faults. The same concept of skew, that is clock skew, signal skew, and then also clock jitter, and then setup and hold time. All of these abnormalities or practical considerations come under what is called as delay faults, and it is called as bridging faults. And we have two types of bridging faults. We have AND bridging and we have OR bridging. Okay. So among all these things, what is important is this: short circuit, open circuit. Then we have transistor, resistor, stuck at 0, stuck at 1. And this is already known. Bridging faults is there, but we are not going to study them. Okay. Now a classic example of logical faults is the resistive short. So we are speaking about resistive short circuit. So let us take example of this thing. So I hope that all of you are preparing for review. So you know that this is a NOR gate. So we see here when I simulate it, then I am getting the output which is justifying the truth table of a NOR gate. Now see here, I am taking output Y NOR at the intersection of drain of P2 and the intersection of drain of N1 and N2. Now for example, on the silicon wafer, if I have a metal blob, so metal blob is nothing but it is metal 1 layer. So I say metal 1. If accidentally a metal blob falls in this particular area on the wafer and then somehow it spreads like this, and it spreads like this also. So you know what happens? What happens is that the output node YNOR now gets connected to VSS. This is called as a metal blob contamination. So here what is happening is that now I told you that every layer, whether it is polysilicon, polysilicon 2 or any metal layer from metal 1 to metal 6, every layer has characteristic sheet resistance, that is it exhibits a non-zero resistivity. So this kind of a fault which happens wherein the output node gets connected to either the VDD power rail or VSS power rail through elements such as metal blobs, then it is called as resistive short. So I can represent the resistive short like this on paper. Now we can draw the schematic for a CMOS NOR gate as like this. So I have here the thing which I showed in microwave can be shown like this. So I have P1, P2, N1, N2, VSS. So if there is a metal blob which falls between the output node, so metal blob falls between output node, then it acts as a resistive short. So I can say this is RM1, metal 1. Okay, so this is an example of resistive short. Okay, so similarly we have transistor on and transistor off also. Here we have transistor stuck on and transistor stuck off. So take example of a 3D planar structure of an NMOS. So we know that an NMOS looks like this. So we have here, we have N plus source, we have N plus drain. So we have N plus drain, N plus source, this is source, this is drain. And we know that the exact structure should actually look like this. Here I have my SiO2 layer, connect, this is normal. This is my normal NMOS. On the other hand, if my structure becomes like this, N plus and N plus, and if it becomes like this because of error in fabrication, gate, drain and source, then this is similar to like this. This is called as transistor stuck off. It is open circuited. This is called as a transistor stuck off or open. Similarly, if this structure gets contaminated in this way, wherein I have the source, I have the drain, and then there is penetration like this, goes inside, drain. It is actually similar to is an example of transistor stuck on or short. Okay. Now we will discuss about stuck at 0 and stuck at 1, which is very simple. First we'll define them and then demonstrate them. So stuck at 0 or SA0. This is not O, huh? Mind. It is not O. It is stuck at 0. How is it defined? So stuck at 0 means what? Stuck means to get stuck, means get connected. So if an input or output gets connected to ground point, it is called as SA0 fault. Similarly, we can define stuck at 1, that is SA1, in exactly the similar way. we can say if an input or output gets connected to plus VDD point, it is called as stuck at one fault. Okay. And what happens means what will happen if this, so these are called as short circuit faults because it is getting connected. So we can say that these are called as short circuit faults. Short circuit faults. Okay. A brief example of AND and OR gate, how to detect a stuck at zero and stuck at faults is very important. So last, how to detect SA0 and SA1 faults. It's very simple. We take example of 3 input AND gate and 3 input OR gate and you will come to know. Yeah. So we consider a 3 input AND gate here. First input, second input, third input, and this is the output. Okay. Now if I want to find out that if my 3 input AND gate is having a stuck at zero fault, what I will do, I will apply logic 1 to all 3 inputs. Okay. I will apply logic 1 to all 3 inputs. So theoretically the output of the AND gate should be 1. Now if there is a stuck at zero fault here at this input. So for example, if this particular input is actually connected to ground because of some manufacturing defect, then while ideally the output of AND gate should be 1, it will actually show 0. So when I connect all 3 inputs of an AND gate to 1, but I still get a 0, that means what? There is a stuck at 0 fault at one of the inputs. Similarly, if I want to detect a stuck at 1 fault, if I want to detect a stuck at 1 fault for the same AND gate, right? So what I do is, again, this is the output. So 1, 1, and if I apply a 0 here, then my output has to be 0. If this particular input has got connected to VDD somehow, then what will happen is I will get a logic 1 at the output. Similarly, if I want to detect stuck at 0 and stuck at 1 faults for an OR gate, I take a similar example. I have a 3 input OR gate, 3 inputs 1, 2 and 3 and the output. Similarly, here, 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 3 inputs and I have the 1 output. Okay. So if I want to detect, so I can say here I can write down SA0 detection, SA1 detection. Similarly, I have SA0 and SA1. 1. Okay. So what I will do is I will connect okay, sorry, 1. So output should be 1. If one of the inputs, or say this input is actually stuck at 0, then I will get output 0. Similarly, for stuck at 1, I will apply 0, 0, 0. So output should be 0. If one of the inputs has got stuck at VDD, it will give me 1. So these are very simple examples, but it becomes more complicated when we want to find out stuck at 0, stuck at false for AND. Clear? Yeah, so we'll discuss about other things later, but this is most important about different. So this is called as fault models. Okay, so stuck at 0 and stuck at 1 are called as fault models. There are others also.